and we'll have plenty of time to discuss. The meeting is over at 1. I have another commitment, but I'm very glad to participate and share with you. We hope to have some of your mindful input, and also the possibility of maybe some collaboration at the academic level for some of our future work. So let me try to do a plane of the, okay. Can you see this okay?
Yes, I see. Okay, yes.
Okay, for some reason I need to move this a little bit. Okay. Okay, great. So this afternoon, we're very glad to share with you some of our work associated to Coulomb-gas sum rules and vortex-Pair fluctuations. Our group is composed of Professor Gary Williams at UCLA, Ming Fan at UCLA, then at UC Santa Barbara. Also, we are going to be missing Professor Charlie McDowell in computer science. He is unable to join us, and myself from UC Santa Cruz. So this has been a collaborative effort from theory perspective, a lot of algorithm and computing GPU time. So bear with us with some of our results that have taken sometimes a couple of weeks to get to. We study simulations of thermally excited vortices in two-dimensional superfluid thin films. And most of these vortex fluctuations have not been very well understood above the phase transition, above the superfluid transition temperature, BKT. So in essence, the reason that this work is important is because correlations of vortices throughout the temperature regime below and above TKT is important for the understanding of rapid quench dynamics. I'm doing the work of admitting a lot of other people on this talk, but okay, so in essence, that's sort of the main core of this work, right? So we're going to be looking into correlations of vortex pairs. We have very little understanding what they are about the phase transitions. And we're going to make this relationship between the Kosterlitz-Thouless theory and the Coulomb-gas theory, elucidating the Coulomb-gas sum rules in particular. So next slide. So in order to have an understanding of this interplay that we're presenting to you, let's look a little bit at what the Coulomb-gas sum rules are, right? And how they relate to the Kosterlitz-Thouless theory. In essence, at the level of interaction of potential energy interaction, they are quite similar and have the same mathematical formalism. So the interaction is really this represented by the natural logarithmic function of the distance between the vortex pairs and also the charge pairs, right, at the 2D Coulomb-gas interaction form. So this is what is represented here. So in this case, Ki, Kj would be the vortex pairs, and in the Coulomb-gas, it would be the electron pairs, right? And the distance between the pairs that we're describing, and for our case, not is the vortex pair. So in a 2D Coulomb-gas, where we have equal plus and minus charges, it has been known that the Kosterlitz-Thouless phase transition is exhibited in these systems as well. But basically the same properties of the superfluid case. And you can feel free to look into this reference, right? Spencer and Fall, like I mentioned, you do one. But in essence, the primary parameters or regions that we are looking into and are interested in describing are characterized as follows. So above the transition temperature, the superfluid density is of course 0, and the dielectric constant is, diverges just from the simple fact that the dielectric constant is just the inverse of the superfluid density. But the vortex-vortex correlation above TKT is believed to have an exponential decay format. So you can think about it sort of like a spring plasma phase. So you have kind of like free electric charge distributions in some sense, sort of a plasma region above TKT. And below TKT, you of course have the superfluid phase, and for which the superfluid density is finite, and so the dielectric is finite. And in this region, it's kind of good to think about it in terms of sort of a dipole pair distribution throughout it instead of a spring plasma, right? And so where the vortices are bound, and so you can think about it in a sense of sort of a dielectric phase. But the most important part to get from this region is that the Vortex-Pair correlation function is really decaying as the power law decay. Okay, so I'm not able to go to the next slide. Where's that? Okay, good. So now having that sort of framework as an analysis for our work, let's take a look a little bit to how the simulations actually look like. So this is a diagram where, well, a slide where we have I wonder if somebody could actually just admit people because I'm not able to do it at the same time as I'm doing the presentation. Okay, so here what we see is simulations of vortex pairs throughout different temperature regimes. So we can see, in essence, this was produced by utilizing 1024 times 1024 lattice spins with Metropolis Monte Carlo, which is updating the spin angles. And now the vortex positions were identified by a plus and minus 2 pi spin rotation about 4 neighboring spin configuration, which we can take a look if you want at the end of some extra slides. But of course, all of these spin configurations are, are mapped utilizing the 2D XY model, right? And from there, we can construct the vortex topological representations. We have that at infinite temperature, the vortex density follows as the theory would predict. So 1/3 per lattice site. And in all of these plots, what you see is the red and blue would correspond to the vortex pairs, right? So vortex and anti-vortex pairs. And so at the face at t equals to TKT, you have them pairs, so they're bound. So bound vortex, anti-vortex pairs. But as we sort of progress in temperature, right? So as the temperature increases, you begin to see an unbinding of these pairs. So you begin to see some lonesome vortex and anti-vortices throughout. And so that's what the theory predicts, right? Sort of a generalized unbinding of these pairs as we go above the phase transition. Okay. Good. So now what people are still coming in. So now what we're seeing here is sort of the most generalized parameter, if you want, the topological parameter that we examine across the phase transitions is what is called the winding number. Right? So the winding number, you can think about it as a kind of a macroscopic variable that describes the counting of vortices throughout different regions. And this is precisely how it is described. So the winding number is the difference between the net positive and minus the net negative of vortices throughout a region. And the net average of the winding number in a neutral system is, of course, 0. However, the net winding number square, which is now defined as the difference of the positive and negative vortices squared, is finite from just the fluctuations themselves. And And what Kosterlitz and Thouless predicted from 1978 and part an additional aspect of the Nobel Prize is that it predicted a relationship of dependence of this winding member square, the net winding member square, at different variations of the temperature region. So below TKT, the net winding member square is believed to be proportional to R, where R corresponds to the radial distance from the center of your lattice outward into a circular loop. And then at a temperature that is greater than TKT, the average winding member square is proportional to the radius squared to R square, so to the area of this region. So the first regime, T less than TKT, has been termed the perimeter law, and the region T above TKT has been termed the area law. Well, what we find throughout all of our simulations is the surprising result that the net winding member square is proportional to the radial distance only. So the perimeter law is really being upheld throughout all temperatures in our simulations. So it would contradict this condition. And so in order to look in more precisely as to how this winding member calculation works across temperatures, what we did is we plot them, right? So we plot the winding member versus the radial distance. So what you can see here is on the vertical axis, you have the net winding member square. And then on the horizontal, the radial distance from the center of the lattice outward. And of course, at a temperature below TKT, at 0.8 TKT, we do see that the net winding member square is linear in R, and that's precisely what Kosterlitz and Thouless predicted. So there's no surprise there. However, when we go to the temperature above TKT, so 3.0 TKT, we begin to see that this net winding member square continues to be linear in R. Right? So this is where the surprising aspect begins to occur. And when we actually do the simulation at T infinity, the net winding member square is also linear in R. So in essence, we can see how the perimeter law is really being upheld throughout all temperatures from below TKT to above TKT. We have other simulations that are below 0.8, but we're just showing some significant temperatures here. Interestingly though, in addition to the fact that all these winding member squares are proportional to R at all temperatures, something a bit peculiar happens at the temperature of 1.2 TKT. And what we see is, yes, of course, the linear relationship that everybody else upholds to, but we see kind of a bit of a sharp increase in the slope. So that's a bit of a curiosity that all the other plots would sort of follow similar slopes. However, in order to look into this, what happens at T equals to 1.2 TKT, we decided to actually plot the slopes, the derivative, if you want, the slopes of the winding member square throughout all temperatures, all the way up to infinity. And this is what we see, sort of an interesting distribution where the slope increases and it reaches about 2.9 at about 1.2 TKT. And then it has a fall off, and then it has this particular value of 2.0 at infinity. So it turns out that when we actually superimpose the specific heat function upon the slope of the net winding member square or the slope of the perimeter law, these two figures coincide. So they both peak about 1.2 TKT, which is where the specific heat of the system itself peaks at its scale for about a factor of 2. But in essence, they hold the same shapes. And from the physics, I think that it wouldn't be too surprising why these two diagrams are similar or even the same place. In essence, specific heat is really corresponding to energy fluctuations in the system. And the winding number is the vortex density fluctuations of the system, right? So, so in some sense, that should be somewhat expected. Okay. So I'm not, okay. But now, in addition to these two correspondences of the specific heat and the slope of the perimeter law, what we are seeing is something very particular, that the slope at the value of at infinity, at T infinity, is 2.0, right? So it turns out that through our theoretical research, we encounter corroborating results from very specific scientist, Professor Dhar. And we really encourage you to look into this paper. We can show a little bit at the end, maybe. But in essence, he predicted that the perimeter law would be upheld at all temperatures, as our simulations show, purely theoretically, and particularly that the slope of the perimeter law would also be equal to 2.0 at infinity. So in essence, we're really seeing that at this level, these vortices are very strongly correlated, even at infinite temperatures. And they're following the perimeter law, so they're abiding to this relationship of radial distance instead of area law. Just as a little side remark here, I wanted to share, Dhar is, of course, an Indian theoretical physicist, and he was just recently awarded the Boltzmann Medal in 2022, becoming the first Indian to receive this honor in joint collaboration of the prize with John Hopwell, for those of you in machine learning and neural networks. So it's kind of a big figure. So, so what do we do about this? We have these correspondences or corroborating results with Dhar in terms of the perimeter law distribution, and also additionally in relationship to the slope in equal to 2.0 at infinity. We really look more deeply into the Coulomb-gas theory now. So, some of you might be aware that Coulomb-gas theorists for quite a while have realized that fluctuations are very strongly suppressed in systems that exhibit long-range interactions. In essence, density fluctuations, thermal fluctuations are just too costly to be dominant in the system. So in essence, the perimeter law would be upheld at all temperatures where long-range interactions are predominant. But what we more specifically found within the Coulomb-gas theory was the Coulomb-gas sum rule, which some of you might be familiar with. So some sort of generalized way to think about the Coulomb-gas sum rule is sort of this relationship between the macroscopic and microscopic parameters of the system. If I understand a system at a microscopic level, I might be able to derive macroscopic parameters from it. So the Coulomb-gas sum rule is able to relate, in this particular context, correlations of vortices below TKT to the slope of the perimeter law. So where Dhar here corresponds to the charge-charge correlation within the Coulomb-gas theory, and in our case, you will begin to see that it also corresponds to the vortex-vortex correlation below the transition temperature. And here is where you begin to see some of those results. So the Vortex-Pair distribution function has been calculated for various temperatures below and above TKT. And we define it as gamma plus minus. Gamma plus minus is the density of plus minus pairs per unit area within our particular diagram at the very beginning of the circle within the lattice of separation between R and R plus TR. One of the surprising aspects that we find in this vortex-pair distribution function results is that they all have a power law falloff at all temperatures, contrary to the belief that there should be an exponential decay at above TKT. But in essence, for the Coulomb-gas sum rule, we particularly see an exact equivalence for the charge-charge correlation function to the vortex-vortex correlation function as following the power law decay. And then for T TK less than TKT. For T greater than TKT, we don't have this equivalence between the charge-charge correlation and the vortex-vortex correlation function, primarily because Dhar is really known to have an exponential fall-off in distance R or above the transition temperature. So what do we do with this? So we have a very happy correspondence between the Coulomb-gas sum rule results and what we obtained for the slope of the perimeter law up to TKT. And then we do not have that though for above TKT. So, and that's precisely what we're sort of pointing out here that where we can actually, map together the perimeter law, specific heat, and then the Coulomb-gas sum rule results below TKT, they agree. But above TKT, we just don't have an analytic form associated to the Coulomb-gas that we can use as a corroborating result. So if any of you have ideas or experts on Coulomb-gas sum rule, that would be great. We'd be happy to hear your points. So we continue on sort of a summarized level. The vortex-pair distributions for the plus minus distribution has an asymptotic power law decay at all T with exponents at a very low temperature. And then for the plus vortex relation, we have an interesting follow-up as exactly to -4. So now what is interesting is that in order to see all of these results just in one single diagram, we decided to have a plot of all these exponents of this power law decay versus the temperature distributions across all the temperatures that we tested. And so what you can see here is that we have an agreement with the results of our parallel exponents all through the TKT regime, up to TKT regime. And then we have a continual increase, which happens at about the specific heat or the perimeter, the slope of the perimeter law peak, which is precisely with the vortex anti-vortex pairs begin to unbind, right? High entropy regime. And then we have a continual fall off again towards 2.0, which in essence really begins to tell us that even at infinite temperatures, these vortices are not randomly placed, they are still correlated. So and it's pretty much what we see in our text here. So peaking the exponents near the peaking the slope of the perimeter low. But of course, you have no theory above TKT, and the exponents decrease towards -4.0 for the charge-charge correlation values. But when we see everybody else fall off at -3.0, that is their signature, we see that they're correlated in this regime at infinite temperatures. So some of our conclusionary remarks at this point, because this work is really in progress, we continue to do more work on this, is in essence that the vortex winding number fluctuations follow the perimeter law at all temperatures, and they're in agreement with two aspects, Coulomb-gas and Dhar theories, and that the perimeter law is really a consequence, ultimately, of the long-range interactions between vortices. And then furthermore, that the peak in the slope of the fluctuations matches with the Coulomb-gas sum rule, right, for at least T less than TKT. and that we find the strong correlations between the vortices even at infinity, so the positions are really not random. And finally, that the power law distribution functions with temperature-dependent exponents are actually sort of a major contribution to the study of quench dynamics through phase transitions. So, okay, somebody else just entered the room. Okay. So now, when we look at these conclusions, and we sort of think about what is the greater scheme that we would want to actually think about in terms of, this group in the understanding of VKT transitions within quantum computing. So there's some interesting aspects in this regard. From one perspective, we have the idea of VKT transitions as research development for quantum computing architectures or topological quantum computing architectures. And this is sort of an interesting venue because instead of looking at, say, electronic charges and their spins as sort of qubits, we can think of this vortex anti-vortex spheres themselves as qubits, as plus and minus ones, from which to encode or upon which to encode information. So in essence, this topological quantum computing aspect is really sort of an approach building quantum computings by encoding the information within the topological properties of the matter within the system. And one of the aspects that has been found as they appear to be more robust against processes of decoherence through the interaction with the environment. So topological defects seem to be a bit more stable, that certain electronic charges utilized as spins as qubits in materials. So in essence, people are really looking into this direction to use this topologies, emergent topologies of vortices as possible information storage for quantum computing. Secondarily, and probably of higher interest, is quantum entanglement. So quantum entanglement has been explored at the VKT transition by scientists in quantum computers. And what they have in essence really done is try to do sort of a sweep of entanglement across the temperature through the phase transition, seeing a peak at the phase transition itself, and then utilizing that knowledge to understand better entanglement within other systems where they are actually performing quantum computations. So for this system, one of the interesting aspects that I would want to put forward, if somebody has some ideas, and we can chat or email afterwards, is lifting up the system to a quantum entanglement calculationable regime. And in essence, at a theoretical level, what that corresponds to is really beginning to look into the sort of von Neumann entropy, right? So we can calculate the von Neumann entropy below TKT, above TKT, and at TKT. We have an idea of quantum entanglement, because quantum entanglement, as many of you are familiar with, really is just the difference in this von Neumann entropy from two separable subsystems. So, so that's something that I'm very interested in looking into for the system. So finally, we would say that scientists are in general investigating how quantum vortices interact, collide, and transform, revealing universal laws governing vortex dynamics in quantum fluids, and that the understanding of these interactions and dynamics could be crucial for the development methods to create and manipulate entangled vortice states for potential applications in quantum information processing and other related areas. So we'd like to thank Professor Dhar for pointing out to us the numerical factor of 2 as the slope of the perimeter law. We also would want to highly thank our team at Hummingbird at UCSC, Ryan Parson and Josh Sandstrom, for really helping us a lot with the simulations. As I said, some of the vortex-vortex correlation functions really could take sometimes days, if not weeks, because we also have to wait for other people's work, but because they can be computationally intensive. Yes, and then we would like to say that this work has been partially supported by the Smear Foundation as well. So now we'll be happy to take a few questions. I believe that in the queue, it's also Professor Gary Williams, you, and myself. And so we welcome your questions.
Thank you for the great talk. And I got a first question from a participant, Jeffers. He asks, how do you define vertex?
Oh, yeah. So, yeah, you could do an AI search on it. It's very fundamental. So these are quantized vortices. They're topological defects. They have a quantized circulation. The one way to theoretically study them is to take a look at, for example, the Gross-Vitebsky equation and solve it. It's just a nonlinear Schrodinger equation, and from there, you can also begin to convince yourself that the velocity of these vortices is the gradient of the phase, and you can become familiarized with the idea of an order parameter as representing the macroscopic wave function that is associated to the Gross-Vitebsky equation. But in essence, they're quantized vortices that emerge in superfluid helium or in the superfluid phase below the transition temperature and exhibit quantum circulation. Yep, next question.
Yes, the second question is, how do you have experimental validation to these results? It's from Marco.
Yeah, sure. I can give that question to Gary if Gary wants to take it as an experimentalist. But there's been hi Gary, want to take it?
No, we really can't access those quantities experimentally. We certainly see the BKT transition experimentally through third sound experiments and torsion oscillator experiments. But to get the details of the transition is much more difficult. You can't access many of these quantities like the fluctuations and the winding numbers.
Okay, great. Any other questions?
I got a third question. How many organizations or institutes you know that are using topological quantum computing?
Oh my goodness, topological quantum computing. I have heard a few talks from Google through the UC Berkeley Quantum Computing Group that have been looking into the BKT and something a little bit more esoteric into Kibble-Zurich mechanism, which is something that we decided to bypass a bit in our understanding here. But there are many folks at UC Berkeley, UC Santa Barbara. UC Santa Barbara has also a quantum computing Google group as well. France, many different places around the world. They're an alternative. They're an alternative to, so for example, one of the other works that I am involved in is in looking at nanomaterials and perovskites, right? So there, what we're looking at is perovskites that would actually be, say, resistant to decoherence. So we have something like cesium lead bromide, for example. We excite it with a certain pulse at its peak frequency. The idea is to have an excitation of the spin up, spin down distribution and see the lifetime of them, right? Well, this lifetime is the picosecond regime, and in order to have, say, successful quantum computing or spin systems that are encoding information, you really want them at the millisecond region. So there's a lot of materials that are very much at the forefront for the traditional quantum computing abilities, but yet topological defects are much more stable against decoherence. So they really do correspond to a feasible perspective and feasible direction. Next question.
Isn't this just sitting a perfect fluctuation vacuum state? This seems impossible.
Could you say a little bit more what you mean by your question?
There's a question from Marco. Isn't this just sitting a perfect fluctuation vacuum state? This seems impossible. You are describing a second order transition. And Marco, can you unmute and ask online? The question is on the chat. So
I can interpret the question in the following way. Vortex fluctuations are thermally excited fluctuations, right? They exist. They happen through in the way that we're presenting them through quench dynamics processes. They've been produced rotating superfluid helium laboratories. Thermally excited fluctuations in the form of vortex states have been in existence for quite a few decades. Not quite sure what he defines as a vacuum state. I mean, that has a very different definition. But vacuum fluctuations, density fluctuations, energy fluctuations, those are significantly different definitions. So we're looking at thermally excited fluctuations, which corresponds to vortex dynamics.
Sorry, can you hear me right now?
Yeah. Hey, Marcus.
Hi. It's Marco. But thank you for talking. And because my question is that usually when you're freezing a material, you see that there's a higher input of energy to actually organize the lattice. So if you're saying that it's going to correspond to vacuum, I don't remember the term they used, but you described like vacuum fluctuations. So aren't you just seeing that perfect state and then that state is failing to decay in an oscillator?
No. So Marco, I think that there's what I was trying to express just a few minutes ago is the difference between corresponding definitions, vacuum fluctuations, thermally excited fluctuations, energy fluctuations. There's a significantly different definitions, different processes. Here, this is a thermally excited density fluctuations regime where vortices are created. We're not exactly at zero temperature, but this is a superfluid state, right? So a particular state of the matter. And so thermally excited density fluctuations exist. They have been known to create in quench dynamics these topological defects, vortex formations, which have been really quite magnificent and peculiar, because what you're having in essence is a large-scale macroscopic system, a superfluid helium state, large and macroscopic, and yet it exhibits quantum effects. It exhibits topological quantum defects. And in this case, they're quantum mechanical because they have quantum circulation associated to them. So your question is outside of the realm of vortex formation. I think your question is more within the realm if we were going to be studying vacuum fluctuations. And you could study vacuum fluctuations in different situations. You could study vacuum fluctuations of the cosmic regime, and you could think about them in that regard. That's an interesting question. It's a different problem. A problem that I'm looking at in the realm of zero-point energy within molecules and what those fluctuations consist in. And other people are looking at it in terms of vacuum fluctuations in the cosmic background. So I think your question is a different question that does not pertain to our system. Next.
The next question is from Robert Becker.
Hey,
From
Robert.
your paper and this first half of the presentation, the results at T infinite are fascinating, though the Coulomb-gas results are most likely not QM in nature, and even the XY model, example magnetized, may not be QM beyond the existence of spin at each lattice point. The existence of the persistent correlation at T infinite suggests only one thing I can think of that has such apparent excess correlation under all circumstances, and that is entanglement itself, are these vortices somehow entangled at T infinite even in quasi-classical system?
Yes. Do you want to unmute yourself, Robert? Can you say your question?
Yes, can you hear me?
Yeah. How are you doing?
Thank you for the invite. I missed the first half of your presentation trying to get signed on into Zoom, so I apologize if I missed anything that would have answered this, but if I can give a little explanation what I'm talking about here. Superfluid helium is obviously inherently quantum mechanical, but I'm not a SME on this, but I don't believe Coulomb-gas is considered to be, is treated quantum mechanically, and maybe even the classical XY model is not. So what I'm looking at is that there are still these correlations, these hard correlations existing at infinite temperature. The only phenomenon that I've familiar with or heard of that might be able to have that kind of a capability would be entanglement itself. And I posed this question before you went on with your presentation to the quantum computing aspect of it. So I wasn't actually referring to that. Is that conceivable? Could there actually be some sort of latent entanglement process involved here that would perhaps explain the persistence of such correlations at infinite temperature? And then if you allow, I had a little bit of a remark on what Marco was saying, because that actually sounds rather familiar with what I was proposing in our collaboration on superfluids. So I'll cut off here.
Sure. Sure. Well, yeah, but Robert, what you're looking at a zero point coherent motion. It's a different question to the emergence of vortices and as density fluctuations. But I'm going to put that aside for now. But I think that your question is rather interesting. So I think that what you're asking, if I understand you correctly, is that the fact that we're seeing this persistent quasi-long range correlations up to infinity, may those be actually a byproduct or a signal of some predominant entanglement at some point? And of course, the picture that I'm getting is, the relationships that exist between, say, so when we begin to think about superfluid theory as sort of a collapsible theory for, say, the creation of cosmic strings, the way that Kibble-Surek would present them, and that within the Kibble-Surek picture, there exists sort of a discussion associated to correlatable events at origination. And that if two events were correlated at origination, then they are inherently entangled. So I think that in some way, if we have a collapse down onto some cosmic strings, theoretical ideas to then, sort of like superfluid vortex dynamics, then I guess your question would say, have these vortices been correlated at the origin of formation? And therefore, this has a signature in their quasi-long range correlation that we find, and more particularly at the topological level, how the winding number square ends up actually being proportional to the radial distance instead of the randomized area law. Possible, but how we go about testing this at an experimental level, I have no idea. Maybe Gary some ideas, but how do we actually begin to say that, how do we trace vortex origination in an experiment and say that they are inherently entangled, and then establish a correlation of that, sort of a origination correlation to an entanglement evolution into T infinity is probably an untrackable problem right now. Does that answer your question?
Thank you for the response. Yes, I was thrown out more speculatively. I don't know of any results or any specific way of testing that, but just to seem to tie in conceivably that maybe there's something underlying going on. I did have one other question unrelated to the infinite one, which is
Can
The
I
existence of
pause you? Can I pause you here? I just wanted to sort of clarify this one point though on the entanglement issue. And it is the following that, so in a way, you're really pointing at this idea of entanglement at sort of this long-lived entanglement that is responsible for this quasi-long-range correlations, right? But there's another aspect I think that gets often missed by a lot of folks that talk about this. And it's sort of like this distinction between entanglement, quasi-long-range correlations or long-range correlations, and coherence. So, and they're distinct definitions, right? The one thing that we can show at this point in this system is quasi-long-range correlations, so spatial correlations as the system evolves. In VEC, people show quantum coherence because we understand that, you know, at the microscopic level, your ground state may be represented as a series of microscopic wave particles in some ways, and they're related by their phase, right? So they're coherent. But entanglement really necessitates separable systems, right? And then show that these are entangled. And that has been a problem. Actually, Richard Packard brought this quite a few years ago. How do we prove entanglement in VEC? How do we prove entanglement in superfluid helium? And I think it's a bit of an ongoing research problem because number one, you have to create separable systems to subsystems. And the way to think about quantum entanglement, you know, sort of the state of the art at the moment is really calculating not, of course, your Shannon entropy, but your von Neumann entropy, so your density matrix in one region, and then in the next separable region. And if this difference is non-zero, then you're proving certain degree of entanglement, not necessarily maximally entangled, right? Not your EPR type of entanglement. And that in of itself, it's its own art form. And so I just wanted to point that out in addition to your discussion of entanglement in the system. Does that make sense?
That is enlightening. I did not know Richard Packard had proposed those
He didn't propose.
ideas.
He was thinking about it. Yeah. I don't know if Gary knows about this, but yeah.
Let me, if I can quickly get one in. I apologize for taking up too much everybody's time here, but the other thing that interested me here is the T equals T 1.18 T sub KT phenomenon. Is there any other kind of it is somewhat surprising that there would be these peaks, maybe even, it's probably inappropriate language, but phase transitions or quasi-phase transitions happening at 1.18 times the actual phase transition. That is a little bit, that seems a little bit surprising. It sort of reminds me of in superconductors, I think high temperature superconductors, when there is some phenomenon that exists below the superconducting transition temperature, but actually seem to have incipient beginnings, I'll call them almost embryological beginnings above the transition temperature, just like here where you're above the transition temperature and these things are happening. Is there any other kind of transition or phase transition going on in these systems beyond the Kosterlitz-Thouless transition that would account for something happening at 1.18 for some reason?
No, I don't think so. Maybe Gary could come into this, but we're seeing peaking at reasonable regions. T goes to 1.2 TKT. Anything else might be something that we need to narrow down our data a little bit more. But in essence, your question is interesting, and unfortunately, I would say it's interesting to me not in this system, but on other systems where you have, say, two, you know, sort of metastable ground states or degenerate ground states. And if those systems go through a phase transition, do we have sort of a, you know, a transient pseudo secondary phase transition happening? But I don't think that we're seeing that in the system. Gary, do you have anything on that? I don't know if you can hear me. Okay, any other questions?
I see Jordan raised his hand for a long time. And Jordan, can you unmute and ask? And the next one is Dr. Itama. Thank you.
Sure. Thank you. I was familiar that UCSB was doing work in this area, but I was not familiar. And knowing that UCLA and Santa Cruz, the Hummingbird team, had an ongoing study. With that said, what is the best way to contact the team with questions?
Yeah, you can contact us. We are the team.
Oh, great.
The Hummingbird cluster is of help to anybody who's doing long simulations or simulations that are also short. But they have really been patient with us because we have had some of the longest term simulations within their collaboration. To the point that at some point when you sort of consider maybe using the supercomputers in San Diego to do some lower simulations, particularly the ones at Infinity. So they're not at all, informed or understand phase transitions or the physics. But they, of course, are the experts on making simulations run faster and definitely putting them into priority in the queue. So we've had a lot of exchanges with them.
Nice. And when you say the supercluster, do you mean the Nautilus down in San Diego, that supercluster?
Yeah.
Or a different one? Okay, great. Thank you.
Yeah, you're welcome.
Let's see, I had a couple of comments in response to the questions about the nature of the fluctuations at 1.2 TKT. The KT transition is unique because it's at 2 dimensions, which is the lower critical dimension for superfluids. And the transition at TKT is thought to be basically an infinite order transition where there's no peak in the specific heat at that point. It's only the gradual unbinding of the pairs that gives rise to this fluctuations, enhanced fluctuations around 1.2 TKT. And that's where you see the peak in the specific heat. And that's where we see this peak in the slope of the winding number squared. So the fact that that happens at that temperature is not really unusual. I also had a comment on Terry Bollinger's comment, which says he's surprised by the mention of cosmic strings. Actually, in 3 dimensions, the superfluid phase transition is due to the excitation of vortex loops. And you can actually, I've worked out the theory of that in 3 dimensions, and I can connect to the theory in 2 dimensions, that the vortex pairs of the KT theory transform directly into the 3-dimensional vortex loops in 3 dimensions. And there's now quite a bit of renewed interest in cosmic strings in the universe and how they relate to superfluid vortices.
Gary, are there some papers on that? That's intriguing. I haven't seen much in cosmic strings for, gosh, decades. I mean, it was a big astronomy at one time, but that was a long time
ago. It lost
But,
favor, and now it seems to be coming back.
Well, they couldn't observe it. I mean, they made
right. It wasn't observed, so people lost interest.
Astronomy,
but it's
now
coming back.
Also, or only in terms of the modeling.
I'm not entirely clear, but I've seen several papers recently and fairly regular papers that have advanced ideas of the relationship between superfluid vortices and strings in cosmology.
And even saying that makes sense because it is the mathematics are similar. I can see that. So, but you've got me intrigued. I'll definitely have to look that up.
Yeah,
and see what
Yeah.
what's transpiring in that on both the math. That's fascinating.
Yeah, I think the mathematics
So
is very
thanks.
much, if I may add a little bit here, I think the mathematics is very similar. I mean, when you look at the Higgs formation and you look at the how do you derive the Higgs and you collapse that from Minkowski space-time into 3 dimensions, you really begin to arrive at the Gross-Koteletsky equation. So it's very intriguing. And in some ways, I think superfluids are sort of a Earth laboratory.
But we are in a chiral universe, and you can't get around that. There's some really interesting stuff going on at that level, all the way down to the Higgs boson. So
yeah, that's so interesting. A chiral universe, you said?
well, yes, it absolutely is. I mean, the right-handed, you have the right-hand, left-handed fermion types, which so often they skip over that, but it's not a detail. When you get into the Higgs boson, you have to start looking at the left-handed and right-hand versions of the electrons. Only the left-handed matter ones interact with the weak force. Right-hand ones are blind to it. There's a stark disparity at the fundamental level there. So these issues are very, very deep.
It's very interesting. Actually, we have a student, a graduate student in our lab. It's a different lab now that I'm talking about. And we're looking at the origin of chirality in perovskites. And we sort of began to ask questions about chirality in DNA. And I saw a talk from the astrobiology group at UC Santa Cruz on, universe chirality and trying to mend the relationships between those. So yeah, that's an interesting question. Thanks for bringing that up.
Chirality and vortices, it's an immediate connection really going on. So fascinating.
Yeah, very nice. Thank you.
I did have another question about just could you talk a little bit more about the stability of the vortices, stability of the topological approach in terms of decoherence? I thought that was an interesting passing comment you made.
No, so we're not thinking that vortices are coherent or decoherent. We're just saying that it appears that from the theory of the emergence of topological defects, there's a greater stability against dissipation of the environment. But we have not tested that. I don't know if Gary knows some of those tests experimentally, but other folks are doing that. Does that make sense?
I think, were you asking Gary to comment on that?
Well, we know vortices can be very long-lived. You can have basically vortices that persist basically trapped in the experimental chamber for many, many hours. So we know that they're quite coherent over very long times. If you rotate a system and trap a vortex on a wire, you can then see that wire unfold over many hours. It will remain but slowly decay. Decays there's a helicopter unwinding about the wire. Richard Packard actually found that. So some very interesting experiments. So they're certainly very long lasting.
So they very much beat the millisecond spin long-lived successful quantum information systems that they are right now. We're going to get to talk about hours.
Right now, I may have misunderstood you. Did you mention the word decoherence when you were talking about that, or did I misunderstand?
No, I mentioned generally that the interest on topological defects for topological quantum architectures are held under the premise that topological defects have greater stability than the way that, say, electronic spins do as qubits of information encoding.
Okay, so you were not talking about decoherence of quantum states of the vortices. You're talking about the coherence, the stability of the vortex itself.
Exactly, yeah.
Okay, I misunderstood. Okay, interesting.
Thank you.
Dr. Itama, I see you raise your hand.
Yes, definitely. And first of all, admiration and full respect to the knowledgeable people. The speaker and the discussion is very high level. And I will I'm from hospital now, so I will allow myself, with your indulgence, to ask very naive questions and maybe even show my ignorance. Question number one, and I have a whole sequence of them. Question number one, where is the charge in the vortex? And what happens to the charge distribution in the vortex as time goes on? Question number two is, I wonder how come Coulomb-gas is like, to me, population view, whereas van der Waals forces may be more individual, and why they're not even mentioned.
I'll give
more. I have
I'll-
more.
Maybe we take it two at a time.
Okay.
Before we forget.
Okay.
So I'll give a first try to the first two. It may be, and I'm sure Gary has a lot more to offer as well. So yes, very good point. So it's not, when we talk about positive and negative vortex, it's not that there's a charge imprinted on the vortex. As you know, the vortex in of itself in its core is empty of superfluid. But it is termed that clockwise rotating vortex is a plus vortex, and a counter-rotating clockwise vortex is a negative vortex. So that's where the positive and negative terminology to the system comes from. Your other question is a very interesting question, because I also study molecular dynamics with a particular interest in water, and their van der Waals is, of course, a primary force of interaction. But what is very interesting about our simulations in this problem for the BKT transition is that we're finding a predominance of the Coulomb force, which in essence would be, I think you have an intuitive sense that why isn't van der Waals coming into play here? But if we're really seeing that the Coulomb force is very strong, and we're seeing it, in the relationship to the Coulomb-gas sum rules, and we're seeing it in terms of the predominance of that perimeter law all the way to T infinity. Gary probably has more to add to this.
Well, it's just the very long range of the Coulomb interaction is the dominant force law. That's the main thing that we're seeing, and it actually plays a very strong role in the fluctuations that we observe, and that has actually been well known in the Coulomb-gas theory folks, but it hasn't been understood in the superfluid community. So I think our work is kind of pointing out that if you want to understand the fluctuations in these superfluids, 2D superfluids, you have to understand the properties of the Coulomb-gas formulation.
We probably have a little bit, just a few more minutes. I'm supposed to take off for another appointment, another talk.
Maybe we have one more question from Marco. What are the temperature domains here? How much is 5.0 TKT?
When I get that there. Could you repeat your question?
Sure. It's a question from Marco again. What are the temperature domains here? How much is 5.0 TKT?
Oh, it's 5 times the transition temperature. Right, so they're just scaling parameters. Any other questions?
Terry has a question for Gary. Do you have any references you could share on your 3D vortices work?
Yes, certainly. I've published quite a few papers actually on the role of vortex loops in the 3D superfluid phase transition. I'd be glad to send you those papers.
That would be great. I was having trouble finding you on Google Scholar for some reason. Your name may be a little too.
I should be there. My paper on the 3D vortices is right at the top of my site papers.
Okay, I'll try again because I actually put in Gary Williams for author and vortices in the title, and or even in the paper, and I got nothing, which is quite.
Okay.
Try another Google Scholar.
Yeah, that's.
I'm on.
Check out Google Scholar there, Gary.
Yeah.
Okay, well, we would like to thank everybody. If Gary doesn't have any other comments to make or any new in this regard, I think that I would like to personally thank the audience and everybody for being present and for hearing our results. And we look forward to communicating further.
Sure.
Thank you for coming. If your question may be forwarded to me, I can forward to Dr. Carla.
And Gary Williams sending you to all of us.
Yeah, thank you for coming. Yeah, we'll have another one next Thursday. And someone say thank you, very enlightening.
Great. It was great presenting and sharing with all of you. Thank you.
Thank you.
Okay. Bye.